My name is Stephan. I'm an ecologist. I did a PhD at Oxford on the ecology of a small deer called the muntjac deer in southern England. And now I work at a college called Schumacher College, after E.F. Schumacher, the economist who wrote Small is Beautiful, where we look at the reasons for the ecological crisis and its resolutions. And one of the first people I met there was James Lovelock. He taught the first course on Gaia. And we became very good friends then, and I began to collaborate with him on some of his modelling of Gaia, and generally just thinking about Gaia and talking about Gaia. And so I've done quite a lot of work with him, and also a little bit with Lynn Margulis, who also was involved with the Gaia hypothesis early on, and Arne Næss here in Norway on deep ecology. It's a very gloomy picture. It doesn't look good at all. All sorts of things that shouldn't be increasing exponentially fast are. One of the most worrying is the loss of sea ice, which is happening as we speak. Of huge amounts of sea ice, both in the Arctic and the Antarctic, but particularly in the Arctic, disappearing much faster than anyone thought. But there are many other things that are going wrong with the Earth. For example, we're deforesting the Earth incredibly fast, particularly in the tropical regions. There's an exponential rate of tropical deforestation. There's huge amounts of water use. So we're now almost drying up rivers, like the Colorado River and other rivers around the world. We're consuming paper at an alarming rate. The number of cars, motor vehicles, are also increasing exponentially fast. I mean, the list just goes on and on and on. In fact, the International Biosphere Program, the IGBP, came up with a series of graphs which show a whole lot of very worrying parameters increasing exponentially fast. So it's a very bad situation. We really are in a crisis. And one thing I ought to mention, one bad thing I should mention, is the loss of biodiversity, which is also so severe now that scientists are talking about us being in the 6th greatest extinction spasm that the Earth has ever known. We're losing species probably 1,000 times faster than the natural background rate of species extinctions. I think if you don't get depressed, you need to see a therapist. I mean, on this issue. There's something wrong with you if you don't get depressed about this. You'll need help to work out why you're not depressed. And I think many people aren't, not enough people are depressed. I think many people are in denial, because our consumer culture just cocoons us, temporarily at least, from this knowledge and from these terrible things that are going to happen to us. Well, this is Jim Lovelock's great contribution to science, for which he definitely deserves about 10 Nobel Prizes. At least one, anyway. And that is that the Earth as a whole is a great system. Now, what do we mean by a system? It means that it's pretty obvious, really, that everything is interconnected. That the land, the oceans, the rocks, the atmosphere, and the living creatures are all connected in one great system. So that anything that happens to any part of the system will ramify through the whole and can shift it to new states, potentially. Well, if we lose the ice caps, then that warms the world, the planet, because you lose the bright ice cover which reflects solar energy back to space. So we get a warming of the planet as a whole. And if the warming becomes quite large, it will affect weather patterns and wind patterns, even as far down as the Amazon. And so the Amazon may receive less water from the Atlantic Ocean, in which case the Amazon will dry out and burn. And the burning of the Amazon will then release carbon dioxide gas to the atmosphere, which is in itself, as you know, a greenhouse gas, which warms the Earth, which will lead to even more loss of the ice further north, and possibly of not just the sea ice, but the ice caps. So the whole thing becomes self-perpetuating. I don't know if Jim Lovelock said this, but his great insight about Gaia is that the Earth is a system, as I said, but there are two parts of it, in a sense. One is the living component of it, that's to say the sum of all life, the trees, the plants, the animals, the bacteria, terribly important, the fungi, and these other creatures called the protoctists, things like algae that we don't really think about very much. So that's the sum of all life. And they have massive impacts on the non-living component of the planet. That's to say the atmosphere, the rocks and the water. And this is a radical proposal. Before Lovelock, the conventional wisdom in science, which now no longer exists, I mean, Lovelock's ideas are now in mainstream science completely. But before Lovelock, the idea was that the living beings couldn't possibly affect water terribly much, or the rocks, or the atmosphere. They had to adapt to these things, but they couldn't really influence them very much. But Lovelock showed how, in fact, living beings do influence the atmosphere, rocks and water. For example, without any life, you can show that there would be no water now on the planet, because living beings, particularly bacteria, are able to keep water around on the planet. And without life, we wouldn't have many of the rocks that we now have. We probably wouldn't have large continents, and it's an amazing thing. We probably wouldn't have large continents. And certainly the atmosphere of the Earth would be nothing like the atmosphere now, which is a highly reactive atmosphere because of the presence of oxygen, which is a highly reactive gas produced by, or liberated by photosynthesis. If it weren't for life, our atmosphere would be like the atmosphere of Mars or Venus, largely carbon dioxide and at chemical equilibrium. So Lovelock says life radically affects and changes the water, the atmosphere and the rocks, but then they feed back to influence which life forms can exist. So we have a feedback, you see. And he went further. He said something surprising emerges as a result of this relationship, and that is that the whole system, the whole Earth system, is able to regulate its surface conditions to within the narrow limits that life can tolerate over huge periods of time. And that's basically the Gaia theory, if you like. This is a completely revolutionary insight in science, at least it was at the time. Now it's completely accepted in science that living beings have a massive influence on climate. They call themselves Earth system scientists, because Gaia has this unpleasant connotation of animism. And you know, Gaia is a goddess, and you're not allowed to have gods and goddesses in science, even though scientists conveniently forget that all the other planets are named after gods and goddesses. But for some reason, we're not allowed to name the Earth after our own, very own Greek divinity of the Earth, ancient Greek divinity of the Earth. So Gaia is a dirty word in science, although that's changing a little bit. It's now taken as a bit of a joke. You can say Gaia, but no one really thinks it's Gaia. But if you talk about Earth system science, that's perfectly respectable. And life has a central role in the Earth as a system. That's completely accepted. Whether there's an inevitable tendency for self-regulation at the level of a planet when you get this interaction between life and the non-living component is still debated. Jim would say that it's inevitable. I guess he would. Many others disagree with that. So Jim developed a model with Andy Watson called Daisy World, which in part looks at the role of biodiversity on a planet. Anyway, it's a simple planetary system. It's a mathematical model in which you have a sun, which increases its brightness as time goes by, much like our own sun has done. Then you have a planet which has severely simplified biodiversity. We may have 30 million species on our planet, maybe more. Say 30 million was an upper estimate. On Daisy World, Jim and Andy Watson placed two species. These were daisies, one kind with dark petals and one with light petals. And there were seeds of both of these daisies scattered around the soil of the planet. There were no clouds. And they both followed a similar growth response, a temperature response. So they would grow similarly according to temperature. There'd be an optimum temperature, and then if it got too hot, they would grow less, and if it was too cold, they would grow less. So it was a sort of bell-shaped response to temperature. Both of them are the identical bell-shaped response. And they set this thing running, and when the sun was small and not very bright, black daisies, dark daisies, sprouted all over the planet, and rapidly spread because they warmed themselves on the planet. And so we got an explosive positive feedback as black daisies took over the space. But then the sun got warmer, and it wasn't quite so advantageous to be a dark daisy, because now if you were dark you were warming yourself up slightly above the optimum. And so now there was a possibility for white daisies to survive. And they helped to cool themselves on the planet a bit more. And as the sun got brighter and brighter, we got more of a mixture of black and white daisies.
This is based purely on Darwinistic evolutionary principles?
Yeah, it is. The equations, well, the daisies compete for space. There's no actual competition function there, but they just compete for space. The ones that can produce more offspring take over more of the planet. So there's Darwinian competition. And then as the sun gets brighter and brighter and brighter, the black daisies begin to disappear because they warm themselves too much, and eventually we have a planet with only white daisies, so the planet becomes totally white. So during the history of the sun, during the time, the evolution of the sun from less bright to bright, the daisy world goes from black and then to dark grey, lighter grey, as we get more mixture of black and white daisies, and eventually as the sun gets really, really bright, it's completely white, with only white daisies. And then when the sun gets even brighter, daisy world can't regulate anymore, and the whole thing dies. Now that's the point. The point is what happens to the temperature of the planet overall during this whole time trajectory. And the extraordinary thing that they found, and this never ceases to surprise me, is that the temperature of the planet always remained slightly below the optimum for growth, despite changing populations of daisies, black and white daisies, and an ever-increasing solar output. In other words, there was a sort of emergent self-regulation which came out of these simple equations. It's absolutely stunning. And it became a kind of toy model or a toy demonstration for how the real Earth could work. And then one thing I did with Jim over several years was to explore the role of biodiversity in this model. So he did some of that himself, but I helped him by making food webs that were more or less complex, that had more or less interconnections between them.
So you explore what increased biodiversity would mean to the self-regulation?
Yeah, that's right. Yeah, biodiversity in the sense of more interrelationships amongst the species, because we had daisies, and then we had herbivores that were grazing the daisies. And we made the connections between the herbivores and the daisies either dense or not dense. So this is more about complexity of the ecosystem rather than the biodiversity. And we found that if you loosen the connections between the herbivores and the daisies, the whole regulation of temperature was much less effective, and it actually oscillated. And as the daisies and herbivores became more tightly coupled with each other, as the richness of interactions increased between the herbivores and the daisies, the regulation of temperature improved.
Biodiversity is actually important to maintain Earth's temperature?
Yeah, I would say that's my speculation, or our speculation. I'm not sure that we've got evidence for that scientifically. We do have evidence on a much smaller scale from some studies on European grasslands and grasslands in North America, that more species in these grasslands lead to better ecosystem functioning, such as nutrient cycling, drought resistance, pest resistance. That's very well established. The project is called the BioDepth Project, and they've got a very good extensive website which details the results. So we know that biodiversity, at least in these grasslands, can stabilize ecosystem functioning, and there's evidence from other small-scale experiments. But at the level of the Earth, it's a speculation to say that biodiversity increases the climate regulation abilities of the planet. So, but I think it does. I think but I can't back that up with data at the moment. To begin with, there was a huge resistance to it. This was back in the early 1970s, when Jim first published a paper, I think it was called Gaia as Seen Through the Atmosphere. And there was a terrible reaction, a very strong reaction against it. Now, why was that? It's interesting to speculate. Partly is because he used the name Gaia, which, as I said before, is not allowed in science. It's taboo to bring up the name of a goddess. You know, it seemed rather animistic. It seemed to propose that the Earth somehow had purposes of her own, that she had a sort of overall consciousness. It seemed rather New Agey, and they didn't like that. But there were other good reasons for criticizing the idea. One was that nobody could quite understand how this self-regulation could happen, because the conventional view was that the Earth is composed of lots of individually selfish organisms, all competing with each other, you know, in Darwinian ways. And how could all that Darwinian competition give rise to global scale regulation? No one could see how that could happen. And it's a good point. We still can't see how it can happen. Not entirely, anyway. Still not clear how it works. The other criticism was that it implied some kind of mysterious consciousness at the level of the planet that was doing the regulating. It's called teleology, the notion that nature has purposes. And as we all know, nature is just meant to be this blind, dead, mechanical thing with no purpose whatsoever. So these were the criticisms that were levelled against the Gaia hypothesis, one philosophical, one more scientific.
So it was a kind of clash of worldviews, actually, yeah?
Yes, it was like a clash of worldviews, yeah. Because science had been progressing along, at least biology had, and geology, along very mechanistic lines for a long time. Of course, not physics. That changed with the quantum revolution in physics and with relativity. But in biology and geology and the other sciences, there was a very mechanistic outlook. Everything was dead. Everything was also fundamentally predictable. It was all the natural processes were linear in the sense that a given disturbance would produce a predictable effect. So a small disturbance would produce a small effect, a big disturbance would produce a big effect, and in principle it was thought that these effects could be understood and quantified and modelled mathematically. Suddenly, Gaia theory was showing that, well, perhaps the Earth, in fact, is more like an organism than it is a mechanism. More like a giant physiology. And perhaps it's more non-linear than people felt comfortable with, that small disturbances might be able to propagate through the system and create large effects, as, of course, happens with our own physiology. So it was disturbing to scientists, I think, to think of the Earth as a kind of organism when they were used to thinking of it as a mechanism. But you can make a good case that bacteria are centrally involved in the movements of the continental plates. I can tell you the story of it if you like.
Yes, please.
Yeah, it's got to do with water, you see, because you have to have water for plate tectonics. The reason is that the water acts like a sort of lubricant.
Yes.
You know, as you probably know, part of the plate tectonics process is the rising up from the mid-oceanic ridges of a sort of semi-molten, very viscous rock from below, from deep below. It comes up, it solidifies and moves sideways. Yeah, and then eventually it sinks at the continental margins and goes back. Yeah, and as this plate of basalt rock moves sideways, it absorbs water. And there are certain chemicals in the rock that just love the oxygen in the water. And they want to get hold of that oxygen, and they do. They strip the oxygen out of the water, and that leaves free hydrogen. Now, hydrogen is so light that the Earth's gravitational field can't hold it down. And so it tries to escape back to space. where it really likes to be. You know, hydrogen likes to be in interstellar space. That's where it feels most comfortable. So it sort of tries to move out. And of course, if you lose all the hydrogen, which would eventually happen through this process and some others, but let's focus on this one, the Earth would lose its water because you have to have hydrogen to make water. The oxygen would be bound up in the rocks and the hydrogen would go off to space. And the Earth would dry out. But this doesn't happen because hydrogen is very important for metabolism. Living things need it to liberate energy from food molecules. And so bacteria in the sediments capture the hydrogen and use it to liberate energy. And by various means they recombine the hydrogen with the oxygen and reconstitute the water. So this means that thanks to the bacteria, water is maintained on the planet. And because there's water on the planet, plate tectonics can continue. And therefore the continents that ride on top of the basalt, seafloor basalt, like corks on top of water, those plates can then move around. And we can have mountain building and volcanoes and subduction zones, all because, well, in part because of what tiny little bacteria are doing down in the seabed sediments and capturing this hydrogen that would otherwise escape to space. This proves, it doesn't prove, but it demonstrates what Lynn Margulis has said, I think, several times, that it's the microbes that rule the world. Of course, unfortunately, now we are ruling the world, but it's really not our place to do that. It's the microbial realm that should be allowed to rule the world. For the last, say, 500 million years, they've been regulating. We've had multicellular life, like trees. Well, trees for maybe not 500 million years, but land plants. We've had recently great forests, and so now multicellular life has joined in the self-regulatory dance along with the bacteria. But when life first began, we think about 3,500 million years ago, basically all the regulation was down to the bacteria for perhaps 1,000 million years. And even after that, we only had unicellular or small nucleated organisms. So the microbes have been, let's call them microbes, have been involved with regulating the planet more or less on their own until the last 500 million years, for the huge bulk of Gaia's lifetime. But there have been crises. There have been, well, let's say radical shifts of the state of the Earth. One of the most radical, you could say, was when life first appeared, must have been a radical shift in the atmosphere as the organisms began to draw down carbon dioxide for their photosynthesis and release methane from decomposition. So we probably had a methane-dominated atmosphere in the early days of the Earth. That was quite a radical shift. And then eventually there was another radical shift when oxygen began to become more abundant. And some people think around 2,000 or 2.6 billion years ago, suddenly oxygen became reasonably abundant in the atmosphere. And that caused a complete reorganization of the microbial biosphere, because quite a lot of the microbes didn't like oxygen and they had to go and hide down in the sediments. And other microbes could appear, the predatory microbes that used oxygen could appear on the surface. So a complete reorganization. So it's not as if the whole of Gaia has remained nice and smooth all the time and everything's been hunky-dory and without too many disturbances. There have been tremendous disturbances from within, created from within the system itself, by the system itself. Huge reorganizations, sometimes caused by internal factors, sometimes by external factors. And the regulation hasn't been perfect either. You know, it's wobbled around. Sometimes dangerously hot, sometimes dangerously cold. It's like almost like a semi-drunken Gaia walking on a tightrope. Sometimes almost falling off into heating and recovering a bit, and then almost falling off into cooling. And she's managed to keep this going for 3,500 million years. And of course you could think of us as the latest disturbance to her self-regulatory dance. And in order to regulate her temperature, Gaia has had to extract carbon dioxide from the atmosphere to compensate for the increasing brightness of the sun over geological time. If she hadn't done this, the Earth would be by now far too hot for life. And she's put the carbon in various places. Most of it has gone into chalk and limestone. And I can tell you about that process if you like. But
most people would probably think of coal and oil.
no, that's quite a small fraction of the carbon on the Earth. Most of it's coal and limestone. The next biggest...
chalk and limestone.
Sorry, what did I say? Chalk and limestone. Sorry, chalk and limestone. Yeah. The next biggest reservoir or box, if you like, or bank account or vault. But it's better to think of it as a kind of vault. It's as if she's trying to put the carbon in these vaults where it can be safely locked away out of the atmosphere. So the biggest is chalk and limestone. The second biggest is organic material dispersed through sedimentary rocks. And the fossil fuels is quite a tiny amount of that, compared to those two.
Why all the fuss then about us using oil and gas?
Because what Gaia has done is managed to bring down the carbon dioxide in the atmosphere to levels that are so low that plants can just about manage to live on it. Because, as you know, carbon is a food for plants. It's a gaseous food that they take in through little pores underneath their leaves, right? It's a gaseous food. So the Gaia has managed to keep the CO2, bring it down as low as she possibly can without killing off the plants, in the face of a very bright sun. Yeah. So if we then open up one of those vaults, take out stored carbon from the Earth's crust and burn it, we then return carbon dioxide to the atmosphere, and we make things much too hot. You could say it's good for the plants in the short term, which it probably is in the short term, but it makes the whole of Gaia so hot that it's a terrible danger for the whole biosphere. I'm not sure if I explained that. You got the idea? Yeah? So it's terribly dangerous. As Gaia needed to keep carbon out of the atmosphere in the face of a bright sun, we're now returning it to the atmosphere, and so we're pushing the Earth into a hot state, which is extremely dangerous for us and for all other forms of life. So the last thing we should be doing is burning fossil fuels, or putting carbon into the atmosphere through any means whatsoever.
But don't the plants just take it out again? Why can't the algae and the plants take it out again?
Well, they can take out a certain amount, but they can't take it all, not at the rate that we're putting it out there. We're putting it out there at a phenomenally fast rate. Huge. I mean, it has happened before. About 55 million years ago, there was a massive release of carbon dioxide, long before we were around. And that was dealt with very slowly, and the sun was slightly less bright then. But at the moment, the biosphere, the ocean life and the land life, can absorb about half of what we emit. The rest of it stays in the atmosphere. And that half then, the half that remains in the atmosphere, then pushes the Earth into a warmer state, which begins to kill off the biosphere. For example, the algae don't like a warm ocean. They do better with a cold ocean. Because if the ocean gets too warm, you get a warm layer of water forming on the top. And nutrient-rich water from the sediments below can't reach the surface, and the algae starve to death. So as we warm the world by pumping greenhouse gases into its atmosphere, the oceans get warmer, the algae begin to die off, and so we lose two Gaian services that they give us, if you like. One is the absorption of carbon dioxide through photosynthesis, and the dumping of that carbon into the sediments at the bottom of the ocean. And the second is the production of clouds, because these algae emit gases which seed clouds, dense white clouds that cool the Earth.
You actually mean that when I'm looking at a cloud that's been made by algae and bacteria?
In part, yes. Not entirely. Some of it's seeded by dust. But yes, especially over the oceans, If you look at clouds over the oceans, they'll be, to a large extent, seeded by marine algae. They release these gases, a gas called dimethyl sulfide, which then reacts with oxygen and nitrogen in very complicated ways to give little particles of sulfur dioxide, sulfuric acid basically, that water just loves to condense around. It's like throwing breadcrumbs into a pond with fish. All the fish just coalesce around breadcrumbs, and then the breadcrumbs are the particles of sulfur dioxide, the fish are water, bits of water. So you get these dense white clouds forming that cool the Earth. And as we warm the Earth, we lose these cooling services from the algae. And as we warm the Earth, of course, the plants begin to have a harder time as well. Water becomes harder for them to deal with. Sometimes, in some areas, if the weather patterns change, they suffer from water stress. And so they begin to die off, they burn, and they release more carbon to the atmosphere, which warms the Earth even further. It looks very bleak. I mean, as we were saying earlier, we're in the middle of a mass extinction right now. So we're losing species. It's like hemorrhaging species, as if someone's cut your jugular and blood's just pouring out. That's how we're losing species now on the planet. Unbelievably fast, as we both warm up the Earth and kill off species that way, and kill them directly by deforestation or overfishing. So the state of the Earth now is, the Earth is in a very bad state. If I would compare it to a social system, it would be like the collapse of the Roman Empire, perhaps. So the Earth is in a state of meltdown right now. It's like that very beautiful, complex configuration that she had evolved into when we first appeared on the Earth, with phenomenal, the highest levels of biodiversity ever seen on Earth. Tremendously complex and rich interactions in the tropical regions, with the northern oceanic regions full of cloud-seeding algae, with tremendous boreal forests and desert areas. All of that now is changing and melting down. We're losing that fantastic complexity. If you talk to some climate scientists, they will tell you that it's severe, but it's not apocalypse, that it's not. There are now inevitable changes, but we might be able to deal with them if we start reducing our carbon emissions now. So everyone agrees that it's a serious situation, but some people think that we can deal with it by reducing carbon, by, you know, these famous wedges by Sokolow, I think it is, that you just energy efficiency, carbon reduction measures, and we can get a grip on it now. There's still time to get a grip. Whereas others, like Jim Lovelock, as you know, say that it's already too late, because the changes now that have been set in place cannot be reversed. One example he gives is the loss of sea ice, particularly in the Arctic, which is disappearing catastrophically fast. And you can do a simple calculation that shows that just the sea that will be exposed to the sunlight, the dark sea exposed to the sunlight, will be in the Arctic Circle once the sea ice is gone. It will be enough to warm the Earth as much as we've warmed it already through our emissions of greenhouse gases, which is a lot. It's nearly 1 degree centigrade. So that's a huge amount. And once that starts, you see, it's a positive feedback. Once the Earth warms, these effects propagate around the entire system. The Amazon forests disappear, the boreal forests march northwards with their dark green leaves and warm the planet even further.
The permafrost.
Permafrost melts. So we end up in this, well, it's called a tipping point, or a series of tipping points, in which suddenly this whole system shifts from one steady state to another steady state incredibly fast, in a non-linear way, very, very quickly. You know, small effects you would have thought would have small consequences, but small effects suddenly propagate through the whole system and bring about catastrophic changes. Normally when we think about carbon or calcium or sulfur or oxygen, they seem to be rather distant, dead mechanical objects, really, that we can't relate to at all. You know, very small, very insignificant individually, and
like billiard balls?
yeah, like billiard balls that interact, but they don't not fundamentally change by their interactions. In other words, it's dead things, and it's very hard for us to relate to them and therefore to the Earth, because they're so critical for the Earth, particularly carbon. So what I've done in my book Animate Earth is to speak of the chemical elements as personalities, and I've studied them very carefully, chemically, to see what those personalities might be like. Because for me, you see, everything is animate. There's nothing that's inanimate at all. Everything is animate. Everything is full of experience and sentience. Following Father Thomas Berry, I would say, like him, that the Earth is not a collection of objects, but a communion of subjects. So the old mechanistic worldview is that the world is a collection of objects, these billiard balls we talked of earlier. But what if the Earth is more like a communion of subjects? In other words, everything has subjectivity, even atoms and molecules, in which case carbon, oxygen, sulfur, nitrogen should all have their own personalities. And I tried to find out what those were by studying the properties of those elements. And I came to the conclusion that oxygen is like the passionate Italian of the chemical world, that it just loves to engage in fiery, passionate relationships with the other chemical elements. And that carbon is like the cooperative Swede of the chemical world. It just loves to make alliances with many other carbons to make huge long chains of carbon. We call these organic molecules. That calcium is a very dynamic princess that loves to get things going and get people excited in the chemical world. So that's what I've done in Animate Earth, and I've developed a version of one of the carbon cycles, the long-term carbon cycle in that book, which retells the cycle in more animistic language. Well, carbon and carbon dioxide, according to this story, become animated personalities. For example, for me, carbon is actually like a prince. I should have said a Swedish prince. A very cooperative Swedish prince. And he's in the atmosphere with his two oxygen courtiers in a carbon dioxide molecule. And he's dying, he's seen the world, seen everything. He's seen the insides of plants, he's been inside animals, in and out of the ocean many, many times. And he's dying for some kind of stability. Meanwhile, in certain rocks like granite and basalt, there lives, imprisoned, if you like, the calcium princess.
How does this relate to carbon emissions and the trouble we have now with fossil fuels?
Well, I suppose you could say that we're, as we said earlier, we're just liberating too much of the carbon that was kept out of the atmosphere by this Gaian process I'm describing. I can go into it if you like, or maybe you don't want me to.
So this is the way the Earth kind of removes carbon from the atmosphere?
Yes, this is the main way in which... Remember I said earlier that most of the carbon that was in the atmosphere is now in the form of limestone and chalk. This is the way that carbon finds its way into limestone and chalk. Because the chemical formula for chalk and limestone is Ca, calcium, C, carbon, O3. In English you call it calcium carbonate. So three of the chemical elements. The Ca is the princess, C, the carbon, is the prince, and oxygen is the passionate Italian. And they're all there together in this chalk. So the question is, how does the carbon get into the chalk? How does it get into this relationship with calcium and oxygen? Well, the story begins with the prince and his two courtiers zooming around in the atmosphere. And he's dying to find his calcium princess, but she is locked deep inside granite and basalt rocks in this crystalline lattice, like it's inside the granite castle, if you like. And so they need a priest to marry each other, and of course the priest is water, rainwater. But unlike human priest that goes home after the marriage, this chemical priest, the water, gets completely involved in the marriage. The three of them sort of get together. And what's released is hydrogen, little hydrogen beings that are so small they sneak their way into the granite castle. They go under doorways, so to speak, through little cracks under windows, and they find they sort of trip past the guards. You can imagine these huge, great chemical guards in the rock, guarding the rock entrances, the rocky entrances to the castle. The hydrogen is so small, it's like a flea. It just goes between their feet, and they don't notice. But the hydrogen has got a positive charge, and this positive charge interferes with the electrical attractions in the rock, and it begins to dissolve, liberating the calcium, the princess. And she can then get together with carbon in the carbon dioxide. And this, very roughly speaking, is how the chalk is made. Actually, what's made is a solution of chalk, not solid chalk. And this solution of chalk is washed down to the rivers. This is the long-term carbon cycle, which regulates the Earth's temperature on geological timescales. And it's a process that will eventually remove the carbon dioxide that we've put into the atmosphere in about 200 to 300,000 years' time. So it's terribly important. It could be what's going to rescue Gaia in the long run.
So this Swedish prince is actually really needs to get into that rock.
Yeah, it needs to get into the rock. It's a very slow process, as I've just said. It takes 200 to 300,000 years. Slow from our point of view, but quite fast from Gaia's point of view. So once the prince and the princess have been washed by the rivers into the oceans, there, little marine algae, in fact, the same ones that produce the cloud-seeding gas, but also the corals or the crabs or any creatures that make chalky skeletons, absorb the chalk solution, make solid chalk, and when those beings die, their bodies sink to the bottom of the ocean, making vast deposits of chalk and limestone. And that's how the carbon prince gets out of the atmosphere. But then you might ask, what happens if this process goes on very effectively? Couldn't it cool the Earth to death? And that is indeed a great danger. We need just the right amount of carbon dioxide in the atmosphere. Too much and we boil to death, too little and we freeze to death, you see. Now this is it's amazing how Gaia has been able to know, so to speak, what the right amount of carbon dioxide is at any given moment. So, as you say, if too much is taken out, if too many of those carbon princes find themselves in the limestone chalk rock, the Earth will freeze to death. So why hasn't that happened? Well, because the great movements of the Earth's plates, plate tectonics that we referred to earlier, actually conspire to subduct some of that chalk and limestone deep beneath the continent, at the continental margin, because they lie on top of the basalt rock, which is coming up from below and moving sideways. Remember, we mentioned this earlier. That basalt rock carries on top of it the chalk and limestone. And when all of that meets a continent, it gets pushed down underneath. And there, the temperatures are so intense and the pressures are so intense that basically the chalk melts and the CO2, the carbon dioxide prince, returns to the atmosphere through volcanoes. And that saves the day. If it weren't for volcanoes, the carbon will end up at the bottom of the sea as chalk and limestone, and the Earth would freeze to death.
But how's the balance here, Harding? Is it when we release now fossil carbon atoms into the atmosphere, doesn't this increase the pace at which these Swedish princes you're talking about are sucked down into the ground?
It does, but remember, it's terribly slow. It's a terribly slow process. So imagine we were to capture a CO2 molecule in the room right now. I've got one here, you know, sort of thrumming in between my fingertips, right? Can you see it? Now I'm going to mark it with a little blue pen and then release it. Now what's it going to do? Well, it'll zoom around in the room for a while, and then when somebody opens the door, it'll find its way out of the door, and then eventually, when someone opens the window, it'll go into the air. And then it might go into a plant, where underneath, through a little pore on the underside of a leaf, and it might stay there for maybe a year or less, or it might stay there, might get into the wood, it might stay there for 300 years. But eventually it'll be returned to the atmosphere. I think on a global level, yes, but probably on a local scale, no. I mean, if you have a nuclear accident of a very serious kind, then it's quite dangerous on a local level. But carbon dioxide is much more dangerous globally. So I think this is why Lovelock is making these statements. And there are other proposals. One is to put sulfate aerosols up into the atmosphere to cool the Earth, and it wouldn't take very much to do it. And we've just had a meeting here at SUM in the last few days in which an American scientist, Ken Caldera, was suggesting that we could even cool specific regions if we wanted to in this way. For example, we could save the polar bears by putting sulfate aerosol above the Arctic, and this would prevent the sea ice from melting. And I think we've reached the point where we are going to have to use such geoengineering, if you like, solutions, although the pipes isn't exactly geoengineering. I used to be against these approaches, but now I'm so shocked by the severity of what's happening and the danger of what's happening to the Earth that I think the time has come for us to seriously consider these options. What people are thinking about is, you're quite right to talk about iron, because iron is one of the limiting nutrients in the ocean. You know, the tropical oceans are basically marine deserts. There is life there, but there's not much of it. And this is a puzzle, because there's quite a lot of nutrients there apart from iron. And if people have tried dumping iron into the tropical ocean, and they find that we get great blooms of algae if that happens. So one suggested fix to the climate change problem is to seed the ocean with iron, so tropical oceans with iron. And then that will produce two things. Well, algae, basically. Sorry, start again. The proposal has been to seed the tropical oceans with iron, just to dump lots of iron in the tropical oceans. This would stimulate algal blooms, and they would suck out carbon dioxide from the atmosphere and produce clouds, thereby cooling the Earth on both accounts.
I've seen calculation that this is quite cheap, actually.
Quite cheap, yes. But putting iron is a highly bioactive element, and we don't know what effects that iron will have down in the deep sediments, where there are very important ecosystems at work. It could really disturb the whole balance down below. So it's not a very wise thing to do. But Jim Lovelock, I don't know if he talked to you about this, but Jim Lovelock has proposed the idea of putting pipes into the ocean. Not very deep ones, just below the warm layer of water that I talked about earlier. Just slightly into the cooler water, nutrient-rich water down below. And wave action would bring this cooler water up to the surface and feed the algae. And the idea is that this cooling would then spread throughout the whole planet through positive feedback. You would start it in a few key places of the world ocean, and then that would cool the region. But then by cooling the region, the cooling would spread outwards, and so the effect would spread globally. Well, one scenario is that we learn to fall in love with the Earth. This is the most important thing that we can do. It could be our first step before we start reducing our carbon emissions. Imagine, sorry, go on.
What does falling in love with the Earth mean?
It means no longer seeing it as something outside ourselves. I mean, take the word environment, for example, which a word I really dislike. It suggests that the environment is something not to do with us, that it's some other thing that surrounds us, but that we are not really connected to. So I don't like the word environment. I haven't really got a better word for it. Perhaps we haven't got a better word for it in English. But we need to realize that we are deeply embedded in the Earth, that we are just as our gut microbes are to us, so are we to Gaia. We are embedded within this great round living creature, though I would say a sentient living creature. It's as if in science we've just discovered a sixth kind of life. You know, I mentioned the 5 main kingdoms of life. Now there's a 6th one, which is life at the level of the whole planet. A new kind of living being, a planetary being, and we are deeply immersed in her. And we need to take on board this idea, and we can use our science, the science of Gaia, or Earth system science if you like, to really develop a sense of deep belonging to the Earth. Because the stories that science has given us, like the ones I've outlined, are so miraculous and inspiring, so awe-inducing, that we can use them to help us fall in love with the Earth.
So one scenario for you is that human beings from now on become devoted Gaians.
Yeah, we've become devoted to Gaia, absolutely. all of us become devoted to Gaia and we work for Gaia, and we realize for who we are embedded in. Can use the science if we choose to help us fall in love with the earth, to really realize that we're living inside our great relative. You know, and we fall in love, we love her just like we love an ancient grandmother or an auntie, or maybe even our parents perhaps. And then we realize that if we're business people, we can think of it like this: we're working for Gaia Inc. This is the boss, you know. The whole Earth system is the boss. Or another way I put it is that we can be Gaia'd. In other words, that the Earth herself is an active agency, almost a psychological agency, a psyche, that can sweep away the illusion of separation that we have and give us this gift of connectedness with her great vast body. So that one scenario is that happens on a mass scale, and everybody then understands the need for reducing our carbon dioxide emissions and for stopping the destruction of wild nature.
So in this scenario, a kind of global love for the Earth motivates to do radical measures on the carbon issue?
Well, we might still need to do geoengineering at this stage, because I can't stress enough how serious the situation is becoming. So we may well need to put sulfate aerosols into space above the Arctic and the Antarctic, and we may well need to use Lovelock's pipe solution. And you may well need to try experiments like this, even though there are risks involved. But the other scenario is, of course, that we carry on with business as usual. Or, not even with business as usual, that we all reduce a little bit and start to feel good about it and think that we're actually doing something. So we just reduce a little bit of carbon here, drive a bit less there, but none of that's going to be nearly enough to solve the problem. And then...
So if the first scenario is Gaia Inc., the second scenario would be the do-gooders scenario? The
do-gooders scenario, yeah. You do good. It's like giving a little bit of money to charity, but you don't really care that much. You just give a little bit now and again.
Reinvestments, cut carbon emissions by 20%.
Exactly. Yeah, sort of half measures, really. Tokenism. And then we end up with very severe, drastic and sudden, abrupt climate change.
When does this happen, approximately?
Well, it could happen. It's already happening. We're losing the Arctic sea ice exponentially fast. Shockingly fast. I mean, this last summer we lost a vast extent of sea ice. Already the Northwest Passage is more or less opened up, and already the oil companies are moving in to try and exploit the oil reserves there, which is the ultimate irony. So it's already happening. I don't think we should think, when is it going to happen? It's happening. We're already losing vast amounts of biodiversity. It's actually happening. The permafrost is already beginning to release some methane. So we're at the beginning of what could become an abrupt change. I mean, many of the scientists involved in this field no longer think of gradual climate change, but of abrupt changes, you know, from one state to another. So we could tip into a warm state very, very quickly. Maybe say within 8 to 10 years, we could begin to see very severe changes. We're already seeing severe weather events around the world. I mean, in Britain this last summer, we had extremely severe flooding. You probably heard about it. There was at least one Force 5 hurricane in the Caribbean this year. Had it struck the United States, it would have made headlines. But of course because it struck Central America, no one could be bothered, because no one cares about Central Americans. They care about Americans, but not about Central Americans. Yeah, and so these severe weather events are happening all over the world. They're also increasing exponentially fast. So it's not a question of when. We're actually in it now, in the beginnings of it now. And so I think the time has come for us to experiment with geoengineering. There's a radical change away from this globalized, so-called free market economy, which is based on the idea that we can keep extracting wild molecules from Gaia for as long as we like, and in any quantities that we like. this idea of limitless exploitation of nature, which is the fundamental assumption in our economic system, would be abandoned. It's clearly unsustainable. And instead we'd move away from that kind of suicidal growth to what I call intelligent growth, in which what grows is, first of all, on a psychological level, love of Gaia, connection to place, a massive relocalization of food production, of industry, and of community. You don't have to be an animist to adopt this. You can be a mechanist, but still understand the need for it. But if you're an animist, it makes it easier, it gives it more meaning, because then the whole Earth and the whole cosmos is fundamentally meaningful, and there's no longer a split between human culture and nature. Culture goes, in this view, permeates everything. Humans have a certain kind of culture, but so do bacteria, so do trees, so do birds, and so indeed does the whole Earth. So this animistic perspective allows us to dissolve the dichotomy between ourselves and the rest of nature. And this gives us fantastic motivation, energy, and satisfaction. So we would relocalize on a massive level. The huge transportation networks that we now require to move food around would disappear. Much of the food would be produced locally. Most of our clothes, most of our industrial products, of course there'd be far fewer of those, would be produced locally. And wild nature would be allowed to regrow. No more of it would be cut down. Our agriculture, of course, would be not like it is now with vast inputs of fertilizers and chemicals. It would be more like what's known as permaculture, which is where you grow lots of different species, all of them useful, together to mimic the synergies that you find in a wild ecosystem. It's been very well proven and highly productive all over the world. And at the same time, we would probably be strongly motivated to carry out some geoengineering. Because as I keep saying, I think the time has come to take radical steps to prevent the runaway warming from getting too severe.
Do you really believe this is some plausible scenario?
I don't think we've got an option. We have to do this, otherwise our civilization simply won't survive. So it's not about going back to a previous state of existence, you know, say pre-industrial existence. It's moving forwards into a new, thoroughly exciting, thoroughly challenging situation, full of possibilities that we haven't plumbed before in our culture. What it'll mean is that we'll have to reconnect not just with the earth more, but with each other more. We'll have to find our satisfaction not so much through our computer screens, but through face-to-face interaction, through storytelling, through music making, through community, and through connection with the earth. All of us will have to be involved who are able-bodied with food production in our local area for at least 1 or 2 hours a day. We'll all have to really allow nature to regrow in our local regions and really develop an intimate knowledge of our local regions. We'll have to create those stories again about, if you like, the spirits in the local trees, about the local rivers, about the local mountains and valleys. We'll have to recreate rich local cultures once more. What I'm trying to do, like many others, is to heal this terrible mistake that we made in our culture around about the time of the scientific revolution, more or less, when we began to seriously believe that the Earth is nothing more than a dead machine. Not just the Earth, but the whole cosmos. You know, when René Descartes' followers cut open live dogs, and the dogs screamed in pain, Descartes said to his followers, "Ignore the screams, they are merely the creakings of a machine." So you can understand what a travesty it is to deny your spontaneous feelings of sympathy for a dog in screaming in pain in that way, simply because you believe it's a machine. So we've believed that the whole Earth is a machine, that the whole Earth is just there for us, that we humans are the only species with sentience, and that everything in the Earth, all the trees, the forests, the rocks, the minerals, are all there for us to exploit, that we've actually been placed here on this Earth to use the scientific method and scientific rationality to exploit the Earth merely for human benefit. And it's no surprise that 400 years later, we now have this tremendous crisis. I'll say it again. It's no surprise that after living under the influence of this worldview for 400 years. No. So it's no surprise that after living for 400 years under the influence of this worldview, that we now have this phenomenal crisis. So we need an antidote to the mechanistic worldview. I don't mean to say we should abandon it, because it's a useful way of seeing the world for certain purposes. It's useful as a tool, but it's not useful as the guiding metaphor for an entire culture. So we need to look for a metaphor that is more appropriate. And in order to do that, we can look either to other cultures or dig down into the history of our own culture, like doing a sort of cultural archaeology, and look for ideas that could serve to become, once again, the appropriate metaphor. And the idea of anima mundi is the most suitable. That comes from ancient Greeks. In fact, they spoke not Latin. Anima mundi is Latin, but Greek. They used to talk about psyche cosmou. Plato writes about this in the Timaeus, psyche cosmou, the psyche of the cosmos. And we've touched on this idea earlier, that the whole cosmos is sentient, that everything is a subject, everything is capable of experience, everything is in some sense...
like carbon princes and
yes.
calcium princesses and algae and...
Yes, all of those things. I mean, I don't mean to say that carbon actually is a prince, or that calcium actually is a princess. I'm trying to breathe some kind of animistic language into the discourse. You could come up with another story. What matters is not the actual details of the story, but the intention and the spirit behind the atmosphere and the relationship that the story evokes when you hear it. If you read a standard chemical text about carbon dioxide, it'll probably send you to sleep. It's incredibly dry and brittle. Very interesting, of course, if you've developed a scientific outlook, but very dry and brittle and incapable of inspiring anyone but the most arcane ivory tower academic. But if you take those same facts and tell them animistically, as I have tried to do, talking about carbon as a prince and calcium as a princess, suddenly you begin to see these chemical elements as beings that relate to each other, just like we do, as beings that try to find satisfaction in their existences, much as we do. And suddenly, in my experience of teaching Gaia in this way, the whole subject becomes alive and becomes three-dimensional and relational, and people can suddenly begin to understand and relate to the world that they're deeply embedded in. And this brings about a complete relationship with the rest of the world, in which you realize that the world is indeed alive, a great organism. And this gives you a tremendous sense of participation in the world, which is empowering and full of meaning. The most important thing now is not what scientists think about animism. It's getting the sense that we're inside a great living creature out into the general public. That it's okay to feel what you feel in the forest. That what you feel, or what you intuit in the forest or out in nature or by the sea actually is telling you something genuine about the world. That the way the light falls on a Norwegian lake, or the feelings you have in the mountains when you're just making your campfire at dusk and you look out onto the horizon lit up with stars, that all of that is a genuine form of communication from the earth, that the earth is actually speaking to you. That's the most important thing for us to learn now as a culture. It's very important for the scientists to do their science, and I wish they would do it in a more animistic spirit. But it doesn't matter if they don't take it on board. It's more important for the general public to take this on board. I don't like the word animism, by the way, but anyway, it's the only word we've got. I can't think of another one. It sounds too much like a cult or a dogma, which it isn't.
And soul world?
Soul, yeah, and soul the world, because anima mundi means, we didn't say this, did we? Anima mundi means soul of the world in Latin. In Greek, the expression was psyche cosmou, the psyche of the cosmos. That was translated by somebody or other in the Roman world into anima mundi, the soul of the world. So we need to re-ensoul the world through telling stories. animated, or animistic, I would say, scientific stories. It's as if we steal into we go into the science department at night when no scientists are around, and we get some of their scientific papers. We steal their papers, and we walk out with these papers, and then we breathe life into them. We animate them with soul. We breathe soul into them and release them into the general zeitgeist of the times. And we allow people once again to speak of rocks and atmosphere and carbon and sulfur and all the other things as sentient, as alive. And that we help people to realize that it's all right to participate with the moonlight on a lake, that it actually is full of meaning and communication. This is what we need. This is the deep inner change that we need. Because without that, we won't have the motivation to make the necessary sacrifices and changes. Because if we don't take on this more soulful approach to the world will force it upon us through wiping out our civilization. This current civilization, with its emphasis on suicidal growth, simply cannot continue. I mean, a 5-year-old child is capable of seeing that. Economists aren't, for some peculiar reason.
Economists would say that it costs like 5% in the long term of the current GDP to counteract the negative influences or the negative externalities of current ongoing growth.
Yes.
I don't believe economists are ready to jump onto the animistic bandwagon just yet, but you think they have to?
No, I don't think they have to. I'd be quite happy if they used that 5% GDP to start putting sulfate aerosols in the air, or try Jim Lovelock's solution of shallow pipes in the oceans. That would be absolutely fine. They don't have to be animistic. Maybe this animism is just my own predilection. I don't want to be a dogmatist, you know. I mean, I have to remember Arne Næss and be pluralistic. So I don't want to go around converting everyone to animism. I'm just sharing my own perspective. But a mechanist could just as well implement the right solutions. 5% isn't much. It means that instead of something costing 100 krona, it'll cost 105 krona. I mean, that's a small price to pay for saving the earth.
Many people feel it's too expensive, and that if we do the growth now, there will be even more money to use for redeeming these or reversing these changes later on, because as growth goes on until people have actually wealthy enough to do these changes.
But what that point misses is the fact that is the point about the timescales and the almost certainty of abrupt shift in the climate. So we won't, before we get anywhere near reaching that level of wealth, were it possible to do so, of course, because it's premised on extracting ever more resources or wild molecules from the earth. But even long before we could reach that level of growth, the climate system would have collapsed into a hot, dry state in any case. So we have to act now. There's no other option but to act right now, immediately. And by the way, I should add that simply putting aerosols into space or using Lovelock's shallow pipes is not enough, of course. Certainly not the aerosol solution, because we'll still have carbon dioxide in the atmosphere, which will acidify the oceans. So we're still going to have to reduce our CO2 levels. Well, I might go further than Jim Lovelock when talking about holistic science, because he means more interdisciplinarity, which is a good thing. You know, chemists talking to biologists, etc. But I take it a bit further. I think what we need to do in science now is put together quantities with qualities. Because in science we made a separation between the two. We said the only thing that counts is what can be counted. And anything that cannot be counted or measured doesn't exist. I.e. the qualities don't exist. The qualities are, as we said before, the feelings and intuitions you have when you're in the forest. These can't be quantified, but you feel them. We've been taught to disregard those and disbelieve them. And now I think we need to create a science in which the qualities are given as much weight as quantities. And we're doing this at Schumacher College, where I work, where we have a master's degree in holistic science, where we explore how we can put these two together. So, for example, we'll work with the mathematics of Daisy World, or we'll make a carbon cycle model, but at the same time we'll work with Goethe's science. and his intuitive approach to plants and to phenomena. And we'll try and put the two together so that our students then become able to use reason when reason is required, but also to use feeling, sensing and intuition when they are required. So they develop all these four ways of knowing in themselves as equally as possible. And then you don't have thinking anymore, you have thinking, feeling simultaneously. So then you end up with a science that's fundamentally ethical, that will not do certain things because they're unethical, such as certain kinds of genetic manipulation or certain kinds of vivisection would not be done by scientists because the scientists would feel the unethical nature of such activities. At the moment in science, anything that can be done is done in the name of science, irrespective of the ethical implications. Scientists are not trained in ethics. They're not trained in philosophy either. They're just trained to be good servants of the mechanistic metaphor. So in holistic science, we try to heal that mistake by focusing on qualities, the qualities of things, these undefinable but nonetheless real communications from the world of meaning. We combine that with our quantitative approaches to the world as well. Well, the air is in some sense, you could think of it as a sentient creature in its own right, one of the organs of Gaia. That's like our skin is sensitive to touch, so might the air be sensitive to our words. Maybe the air is listening to us in some sense, not in the sense that human ears hear, but nevertheless in some mysterious way carrying our words and thoughts into itself around the world.
Well, it is actually carrying our words in waves, isn't it?
Yes, that's right, it does, yeah. It mediates, that's right. Without air we can't have sound. Mm. So the traditional peoples of the world have always spoken of the air as a kind of spirit that connects everything. So this gives us a more meaningful approach to the air, which is not in the slightest bit against or contradicts our scientific understanding of the air. Not at all. In fact, the two mutually enhance each other. I mean, how wonderful to know that the air is 21% oxygen, 78% nitrogen, etc., etc. You know, to actually know how many of these chemical personalities there are zipping around in the air right here. But also to feel that the air has these more magical, mysterious qualities of perhaps a sort of memory or a soul that connects the whole world. The two are completely consistent with each other. Well, let's talk about light. I think light's easier to focus on. See, and we know this, I'm using some quantum physics here, so it's not all entirely sort of fantasy. We know that what happens when light strikes an object is not what Newtonian physics says it is. Newtonian physics says when photons strike a surface, they bounce off. And the photon is fundamentally unchanged. You see, it's the billiard ball view again. Actually, that's not what happens. What happens is, when a photon strikes a surface, it's absorbed by the surface, and it also it disappears into the quantum void. And then a new photon is reconstituted and emitted by the surface. So that's what happens with reflection. So imagine that a photon is striking a green tree. Lots of photons are striking the tree on a sunny day out in the Norwegian forest. Then the photons are going deeply inside the tree, maybe beyond the tree into this quantum realm, where perhaps they absorb the very essence of treeness itself. And then this essence of treeness now saturates the new photons that are emitted. The new photons are actually tree photons, and they're vibrating treely, if you see what I mean. They then go into your retinas, where they transfer that treely information or that tree sensibility into your whole organism, and so you become tree yourself. So in this sense, light could be a form of communication, deep communication, like glue almost, that glues us to the world and is a channel for meaning between different beings in the world. This is how I see light. Everything is full of qualities. Everything is a subject. And light is one way in which these qualities travel from one being to another, through our eyes, but also through the air, through sound. I haven't thought about it much with respect to sound. I've thought more about light. But I think there's more and more dissatisfaction amongst young people who are interested in science. They feel more and more that there really is something missing in science. That there's, like I felt when I was a young student, that I loved the science, but I felt that there was something indefinable, something I couldn't put my finger on, that I wanted out of it, that I couldn't get, and I didn't know what it was. I also found the neo-Darwinist interpretations of animal behavior, based on the notion that everything is selfish and is only out to maximize its reproductive success, thoroughly dissatisfactory and almost abhorrent, morally abhorrent.
You studied deer populations, as far as I know, in your PhD.
I did, yeah.
How was the qualities there? How did you treat the qualities in your PhD?
I wasn't allowed to say anything about them. And I remember the qualities taking me by surprise. I wasn't expecting to find them, because I worked on these small little Chinese deer called muntjac, which I fell in love with when I saw them in a wood in southern England. And I used to spend time watching them ruminating, sitting down with their legs tucked up. And they'd close their eyes, and they'd go into a very meditative state. And a little bolus of food would come up their esophagus, you could actually see it, into their mouths, and they would start to chew very quietly. And I would sit there watching it, and it was as if a kind of incredible atmosphere of calm and peace would radiate out. Very hard quality to describe. It felt a bit like chamois leather, a very soft, leathery, yellow, warm quality would engulf me as I watched them ruminating. And I became totally captivated by this, totally surprised. I wasn't expecting to find this. And they taught me about a soft, gentle approach to the world, just a total quiet relaxation, a regurgitation of thought, of the day's events, of the events of one's life, a chewing over and a re-swallowing down into the unconscious. So I sat there, engulfed in this atmosphere, and I would, then they'd get up and walk off, and it'd take me a while to snap out of it. And I thought, good God, what is this? This is something completely real. And then when I was in my wood, which luckily for me was an ancient woodland, not touched by people for many decades, I would spend hours putting out quadrats to count plants in, to see which plants the deer had been eating, etc. And then, tired of this, I would lean up against a tree and just allow myself to be absorbed by the sound of the wind, by the sight of the leaves, by the whole breathing forest. And suddenly it seemed to me that I connected with the quality of that forest. There was a great personality sucking me into itself through the breath of the air, through its leaves, through its bird song, through its colours. It was just welcoming me into another quality, different to that of the deer, but connected to it, but a more leafy, woody, airy kind of quality, with lots of tentacles feeling into the air. And I would be absorbed into that quality for maybe an hour or so. And then again I would snap out of it and think, oh my gosh, I'm meant to be measuring and doing quadrats. So again I would go through the really difficult exercise of having to put down quadrats and count things. So I ended up with a great mass of numbers sucked out of the forest, almost as if with a vacuum cleaner, sucked out into my notebooks and then into my computer programs that I wrote for analysing the data, and then into multivariate statistical analyses, which told me a great deal about the deer that I couldn't have found out any other way. So I'm not trying to denigrate that. It was an incredibly useful exercise. I found out some very interesting things about how they used their home ranges, the shapes of their home ranges, when they were active and when they were inactive, what they ate. Tremendously useful. But all of that had to be written up in a very quantitative way, a very dry, objectivist way, and interpreted from a neo-Darwinist perspective. So I had to explain why the deer were doing things, or rather why the genes within the deer were making the deer do things. And the qualities that I'd felt were irrelevant. In fact, I didn't speak to anyone about them. I noticed them, but I did nothing with them, because there was no room for them. It was only later when I went to Schumacher College and began to work with colleagues there on holistic science that I realized that these qualities were actually as important as the quantities that I'd abstracted from the living world. So now I can see the need to put the two together. So in my dissertation, if I'd been able to do that, I probably would have tried to describe the qualities, maybe through poetry or painting or art or some other kind of artwork, or maybe through a more poetic a kind of prose, and I would have interweaved that with the quantitative data. I mean, if you take this to its extreme, you can have quantitative data expressed poetically. I don't think anyone's ever done this before, and it would be a jolly nice thing to read, instead of these dry academic dissertations like mine that nobody ever bothers to read. So there's no need to throw away the quantities. The quantities can be brought to life through a connection with the qualities. And this is what we're trying to do in holistic science.
And this is the way the future would turn if Gaia Inc. and the love of Earth, as you're talking about, becomes a future?
Yes,
future?
and it might have been the way science had developed around the time of Descartes, had it not been for a deliberate effort to repress this approach to science. It could have become a much more integrated form of science. And I think it, well, who knows if it'll become the way of science in the future. That remains to be seen. But there's always that potential.
So, for political reasons, Goethe lost and Descartes won. Is that your...
As to put it crudely, yeah. Or, Descartes wasn't as bad as we think he was, actually. You know, he was a very religious person. And he had his reasons for saying the world was a machine, more for political reasons. But anyway, yeah, to put it starkly like that, yes, Goethe, we would have had it wouldn't have been Goethe 0, Descartes 1. It would have been 1 all. You see what I mean? It would have been both together. The mechanistic, quantitative approach blended with the qualitative approach, and each used appropriately as required. And this would have given us an inherently ethical science, and therefore a completely different world. I mean, I remember a lot of my colleagues at Oxford when I was a PhD student, my fellow PhD students, offline would confess to these feelings, and we all loved the animals we were studying. You know, I had people, some of my friends studied capybaras, others hunting dogs, you know, some really exciting animals. Some of them not so exciting, rats and things, but they all had a love of the animals. They all wanted to, they were doing it really to gain some sense of communion and meaning, to find some kind of meaning. But as soon as we got into public discourse or into dissertations or scientific papers, all of that was forgotten. And it was, you know, the usual neo-Darwinist approach. So it was semi-conscious and not developed and not brought into the practice. But you're right, I think all scientists are like this. I mean, most scientists will admit to the importance of intuition in interpreting data. They'll suddenly have a hunch about what a whole load of numbers mean, but they don't cultivate intuition.
Since Albert Einstein, that's a difficult thing to deny, huh?
That's right, yeah. He was a deeply intuitive scientist, and Lovelock too is deeply intuitive. And in holistic science, we cultivate the intuition through, one way we do it is through a very careful observation of a plant, let's say. We draw the plant very carefully, and then we close our eyes, and we imagine how the plant took shape, how it shaped itself into its fully grown form from the seed, how the seedling developed, how the leaves came out. And this teaches us to think like a plant, to think dynamically. And if you do this properly, you can get an intuitive insight into the nature of the plant, and indeed beyond the plant, into the dynamic nature of being itself. So it's a very, very powerful method for awakening your intuitive powers. And then you can bring in the quantitative aspects if you want as well. You can make mathematical models of the development of the plant. And then you end up with a truly holistic understanding that satisfies reason, feeling, sensing and intuition simultaneously. I relate to Gaia by finding a place that's as wild as possible. That's to say, as far away from car noise, machine noise, lawnmowers as I can. A place that's been as little disturbed by humans as possible, and just dwelling in such a place for as long as I can. The best thing for me is actually to escape from Britain altogether and come to somewhere like Norway, where the landscape is much, much freer of human influence, where everything around you, one feels, is more doing its own thing, irrespective of human intervention, although I know, of course, there is human intervention here. That's what I need to really be myself fully.
That could sound a bit anti-human, as if you try to avoid the humans. Are humans evil?
No, not in the slightest. Humans are a wonderful, fantastic species, just that we've got slightly rather out of control. There are too many of us, and we're having too much of an effect on the world. No, but I'm not anti-human in the slightest. I think humans are a wonderful species, but no more wonderful than any other. We're just as wonderful as bacteria. Just imagine, without the action of the bacteria, there'd be no nitrogen cycle. Without a nitrogen cycle, well, we couldn't exist. So the microbes are just as wonderful as we are. I like the phrase of Aldo Leopold, we humans are just plain members of the biotic community. We're just plain members. We're not masters or stewards, we're plain members of this great community. And in fact, we can't feel fully human unless we sense that in ourselves. So we're a wonderful species. Our role, I think, is to celebrate Gaia, not to dominate or control her. I mean, I imagine skyscrapers would be draped with greenery. There's a Frenchman, I can't remember his name, who grows plants on the sides of skyscrapers. Factories would be smaller scale, with living machines inside them, with plants inside them, and the workers would work only a few hours a day and then spend most of the time tending the gardens outside in the factory, because we wouldn't need so many industrial products. So everything would be suffused with this Gaian sensibility.
Being guided, what's that?
Well, see, people often say I was inspired by nature, or I felt great when I was outdoors. But I think it goes further than that. I mean, for me, the Earth is a great intelligence. It's actually a psyche. I'm not using that metaphorically. I think the Earth actually is a psyche. And it's not just me who thinks this. I mean, many traditional, in fact, I would probably say all traditional cultures have said this about nature. It's actually a great psyche. Remember Plato's psyche cosmou. So we had it even in our own culture before the scientific revolution. So if the Earth is indeed a great psyche, then it's possible for knowledge and intuition of that great psyche to sweep through us. It's possible that it can sweep away our habitual patterns of thought, particularly in these times, our mechanistic patterns of thought, in which we think the whole Earth to be nothing more than a dead machine. It's possible for all of those thoughts to be swept away by this wider understanding of the Earth as fully alive and as a psychological entity. So if I say to you, I was Gaia'd, it means that it wasn't that when I had an important moment in nature, let's say, it wasn't that I projected something out onto nature, which then I felt was grand. It wasn't a projection. It was the other way around. It wasn't a projection from me to the world. It was the world projecting itself into me. So the world is actually an agency with that kind of power, with the power to sweep away and shake habitual patterns of thought. This happened to an American called Aldo Leopold. He's written about this in a beautiful chapter in his book, A Sand County Almanac. The chapter is called Thinking Like a Mountain. And basically, he was involved with wiping out wolves in the United States using the scientific method. And one day he went out into the Gila wilderness in New Mexico with his friends, with rifles, and they sat down to have lunch. And when he sat down to have his lunch, Leopold was still in that mechanistic worldview that we've described earlier. He really thought that we humans had the right to control nature and therefore to exterminate wolves if we wanted to. And then they saw some wolves at the bottom of a river. They were sitting on a cliff and they saw some wolves and they began to shoot at this pack of wolves really excitedly, and they killed several of them. And they scrambled down a scree slope to look at one large wolf that was dying. And Leopold said something like this: there was something new to me in those eyes, something known only to her, the dying wolf, and the mountain. Something known only to her and the mountain. And then it's something, he said something like, I thought that because fewer wolves meant more deer, that no wolves would mean hunter's paradise. but after seeing the green fire die, I sensed that neither the wolf nor the mountain agreed with such a view. And then after that, he began to say things like, we humans are just plain members of the biotic community. Or, a thing is right when it tends to preserve the integrity, beauty and stability of the biotic community. It is wrong when it tends otherwise. He developed what he called his land ethic, in which he said, we have treated the land as a slave. That's morally wrong, just as it's wrong to treat other human beings as slaves. So what happened to him in that moment must have been pretty big and pretty important if he could shift from that mechanistic worldview which he had before he sat down to have his lunch in the Gila wilderness on that bright sunny day. Something must have shifted him very, very radically during that experience with the wolf for him to then go on to develop this land ethic, which he did for the rest of his life, by the way. And what happened, I think, is that he was Gaia'd. In other words, he knew that the mountains, the air, the microbes in the soil, the cactus, the rocks, in fact, all of the animate surroundings had witnessed what he had done and had disapproved of it intensely. So he witnessed, he knew the surrounding environment to be animate and sentient and disapproving, because he says, neither the wolf nor the mountain agreed with such a view.